We have one remaining issue to relate path independence of a vector field and um, and whether a vector field is conservative. So we saw that if we have a vector field that's conservative, then line integrals for that vector field are path independent. And it would be great if this implication went the other way. If we had a vector field that we knew where all line integrals were path independent, if we knew that there was a potential function for that vector field. So let's see if we can make that happen. Now, the only 100% reliable way of detecting whether we have a conservative vector field is to construct a potential function, to actually write down a formula for the potential function. And in this situation, right, assuming that we have a vector field with path-independent line integrals, writing down a formula for the potential function, that should seem like a tall order, because right, we don't actually know what f is. We know that it has this special property that it's path independent, but we don't have formulas for a capital F. So how could we hope to define a potential function for it, or find a potential function for it? To define a potential function, we're going to have to use the only thing we know about the vector field, that it's path independent. So what we need to do is, for x comma y in the domain of capital F, we need to define little f of that point. Okay, and this is the hard thing. So what we'll do is choose a single fixed point. In the domain of capital F, and I'm going to write it as if it's the origin. It doesn't have to be the origin, especially not if the domain doesn't contain the origin. It could be any point, but it's just a point that we are picking for once and never changing. Okay, so given this point that we've, this fixed point, remember, we need to define what little f of x comma y is. And what we will choose is the integral along a curve of f dot dr, where c is any curve from the origin, right, our fixed point, to x comma y. Okay, now in general, this would not define a function, because usually different choices of curves would give you different values for this line integral. And so this function wouldn't be well defined. But for this particular vector field, because it is path independent, we know that this line integral will not depend on the particular choice of curve. It only depends on the endpoints. But to define x comma y, we aren't changing either of the endpoints. We're keeping fixed the endpoints when we define little f of x comma y. So this defines a function because capital F is path independent. All right, so now we have a function. The question is this a potential function for capital F? And that's actually the hard part. That's the hard part of this whole thing. So what we hope, so capital F, right, it's m comma n. And what we hope is that partial f partial x is equal to m, and partial f partial y is equal to n. If you were in higher dimensions, you just have more coordinate functions. All of this would still work. So these are the tricky things about figuring out what are these partial derivatives. Again, if we had a formula for little f, working out this partial derivative would just be calculating a derivative. But since we don't have a formula for little f, figuring out this partial derivative is actually going to be tricky, right? Because we'll have to use our definition of the function little f. Okay, so so what we will do to we'll calculate this, partial f, partial x. Figuring out partial f, partial y is essentially the same, but just in a different direction. So I'll only do one of these. You can work out the other one if you want. So what we need to do is figure out, so here in the domain of f, what we need to do is figure out what is the partial derivative at a single spot here. So what I'm going to do, I'm going to call this spot a comma b. And remember, the origin is somewhere else in the domain. And what I'm going to do to figure out this derivative is I'm going to, right, remember f of xy is given by this line integral. So to compute this derivative, I need to know something about the value of the function f on a bunch of points near a comma b, but varying in the x direction, like this, right? But knowing that this function, knowing that this integral is path independent, lets me choose any path to get up here. And so what I'm going to do is choose a very specific path, right? And the specific path is this. First, we will go from the origin over to here. So this spot is just a little bit to the left of our target, a comma b. So we'll call this maybe, its x coordinate is a little bit less than a. So let's call it about a minus a little bit. So a minus c, comma b. And then, so that gives us this first curve. So let's call that R1. And then then we can go directly to the right through this point a comma b. So let's call this part of the curve R2. Okay, now for x near a, f of x comma b will be the integral along this curve, along first R1 plus the integral along R2 dot dr, right? So this first integral gives us this part, and then the second integral goes sideways until we get to whichever spot we're going to. So I clicked something again. Okay, so now we can evaluate a partial derivative by differentiating this. Well, first let's finish parameterizing this. So this is going to be, this part is just some constant. I shouldn't call it c though. Let me call it capital I for integral. Okay, plus the integral. So what we'll do is actually write down a parameterization for R2. So R2, it starts in the x direction, it's going from a minus c over to this x coordinate. So the y coordinate is b, and the x coordinate, well, we can just call that t, right? And then R2 prime is now 1 comma 0. And the integral for R2 is from, t has to go from a minus c up to x, right? F dot 1 comma 0. dt, right? Okay, so this is some integral that is this first piece plus the integral from a minus c up to x of f. Well, f is m comma n. So m comma n dotted with 1 comma 0, that's just m dt. All right, so this is f of x comma b for x values near a. Okay, well, now we can differentiate this. So all of this was so that we could take the partial derivative of this with respect to x. Okay, when we take the partial derivative of this with respect to x, this integral part, well, it didn't depend on x. So that's just 0. So what we need to do is take the partial derivative with respect to x of the integral from a minus c up to x of m, and m is right, our parameterization was up here, it was t comma b. So t comma b. Okay, oh, and let's evaluate this at x equals a. Okay, so when we evaluate this derivative, well, the fundamental theorem of calculus says that if you do this definite integral with the variable x in the upper bound, and then you take a derivative with respect to x, the integral and the derivative undo each other, and you just get capital M of x comma b, right? That's the fundamental theorem of calculus. They undo each other, but then you stick this in there. But remember, we still need to evaluate this at x equals a. And so we get capital M of a comma b, right? So what we just found is that the partial derivative of this function, little f, is m. And that's what we wanted. So now if we reproduce this whole big calculation for the other partial derivative, we have to go through this whole rigmarole of carefully defining this path that goes over here and then straight up. But if we do that, we get the corresponding thing that partial f partial y is n of ab. So this shows us that f, the gradient of f, really is our vector field capital F. And so we've successfully constructed a potential function for capital F. So that means that f is conservative. So this idea we had that since a conservative vector field has path-independent line integrals, maybe it goes the other way. It does go the other way. In this very, very general situation, at no point did we actually write down formulas for what any of these things were, but still we were able to construct a potential function for our vector field.